But then the volume will explode, huh? Okay. Okay. So I will briefly review what we did yesterday in the context of the aldane phase. And then we will proceed and do a couple of things. We will try to get further insights on this aldane phase very quickly by using cartoon wave functions, what is called AKLT state. And this will help us understanding the connection between the aldane phase and the presence of edge modes. And then I will discuss how this phase can be observed in cold atom systems. And I will give you two examples on how this can in principle be done. We will see pros and cons of each of the examples that we treat. And finally, I will discuss also detection schemes, which is one of the key features in particular in the context of the string correlation functions. So once this is all done, this is more or less the first hour, we will move towards topological superconductivity, which is then the last topic, and will last the second hour today and tomorrow. Okay, let me briefly review what we did yesterday. We focused on antiferromagnetic Heisenberg models in one dimension. And first provided an argument such that for integer s, there is a finite mass gap. And then what we have been discussing is that for a very specific case of s equal to 1, there is a non-local duality transformation that allows us to identify what is called a hidden Z2 cross Z2 symmetry. Okay. And the key point about this hidden symmetry is that once broken, it was possible to identify that by looking at this string order parameters. Actually, I think we wrote them something like this, which in the dual form they were just the antiferromagnetic order parameters of these transform spin operators, and as a function of the original spin operators, let me put alpha here because then all the three are the same actually. Okay, alpha. What you have is something like this. Alpha I exponential I pi sum k from I plus 1 to j minus 1 as k as alpha k as alpha j, okay, which were characterized in this phase. I would like to give a very simple interpretation of what this stuff means, okay? Because in principle, you would like to see, okay, we have very simple understanding of symmetry breaking. I mean, is there a simple way of understanding a phase of matter which has this kind of order parameters? And actually there is, and you will easily convince yourself that the only thing that this stuff really does, it wants to create an antiferromagnetic order, but it does not care if there are zeros in the middle, because these zeros will not contribute to that. So if I have two spins for a distance, at large distances, the only thing I want is to have something antiferro, and I want to have nothing in the middle that disturbs my order, so no pluses or minuses, unless they come in such a way that this string gives contribution 0. So in the middle I can have whatever zeros, and if I want to have something that does not disturb this thing, I want to have something which comes in this order. Minuses and pluses. Okay? I'm not allowed, for instance, to have something which in the middle has, I don't know, several pluses. Okay? By just looking at these cartoon states, it takes quite some time, so that's why I'm not doing it. But just looking at these cartoon states, you understand that this is nothing but a very dilute antiferromagnet. Okay? This is the picture of dilute antiferromagnet. And somehow the rule of this antiferromagnet is that after a plus, there is a minus. After a minus, there is a plus, and so on and so forth. And I do not care about the number of zeros that I have in the middle. Okay? This can be whatever number. This string does not care. So that's why this has to have some kind of hidden order. Okay. Now, in order to have further insight on this Haldane chain, it's actually worth mentioning a model that was introduced a few years after Haldane. This is called bilinear biquadratic Heisenberg model. Actually, this is a spin chain, and this is fixed with s equal to 1. This is where we're interested, the spin that we're interested in. And this model reads as follows: as a sum over I, let me fix j equal to 1, so that we fix the normalization, and then we have si plus 1. We have the conventional Heisenberg term, and then we add minus beta, a term which is of this type, si plus 1 square. Okay? Now, do not wonder what this means physically. Okay, this is just a model. For instance, physically will be a very exotic 4-body local spin interaction. Now, this model has some important features. I mean, the first feature is that if you put beta equal to 1, this is one of the models that was mentioned yesterday, introduced by Takajan and Babujan, and this model is gapless. Okay? However, there is a more interesting point, which is when beta is equal to minus 1/3. Okay? Where beta is equal to minus 1/3, you can show that this Hamiltonian is actually exactly equal to 2 times the sum over I of the projectors between of the pair I plus 1 on the state with spin 2 minus some constant, which we do not care about. Okay. You can just show it by direct computation. This is just projectors. Now, an Hamiltonian which is made out of projectors has several very interesting and very useful properties. First, let me take out this constant for a moment. What is the ground state energy of an Hamiltonian made in this form? For sure it cannot be negative, right? Because all of these guys, they give positive contributions. You're not guaranteed that there is a zero energy state, because these guys might not commute. But if you find a state which has zero energy, this has to be one of the ground states. Okay? And then, eventually, if you find this state, on the top of that, it's very easy, sometimes, not always, but it's very easy to create excitations. So to understand what is the structure of excitations. Now, this was actually what was studied by 4 gentlemen, Affleck, Kennedy, Lee, and Tazaki, and they found out what is actually the ground state of the model, because they showed that there is a state which is annihilated by all of these projectors, so has energy 0, and they also showed that this is unique, which is something which is non-trivial. And this state is actually made in this form. Maybe take... let me write it pictorially. Now, what you can imagine to do, you take every side, and at every side, you decouple the spin 1 into 2 spin 1/2s. Okay? Obviously, when you do this operation, you have to be careful that at the very end you want to project back into the space where the spin 1/2s recombine into a spin 1. Okay? Now, what you can show in AKLT is that you can write a state where the spin 1/2s are coupled in an alternating fashion. And this state is actually the ground state of this bilinear biquadratic Hamiltonian for this specific value of beta. Okay? Now, this state can actually be written as what is called matrix product state of fixed dimension of dimension 2. Okay? But I will not write formulas because this is not our point here. The important thing that you notice is that when you just draw something of this type, you notice immediately that there is something bizarre happening at the ends. Okay? Because of the ways I have arranged my spins, I'm left with one spin ampere on the left side and one spin ampere on the right side. These are now spin 1/2s. Okay. Now, this is obviously a trick because I'm using now open boundary condition. If I close my chain, instead, I just have to recombine these two. So out of this just visual representation, we can argue two things. That in case of periodic boundary conditions, the ground state is unique. Okay. And instead, if I have open boundary conditions, I have two modes that live at the boundary, which are localized, and they are spin 1/2 modes. Okay. Two gapless. And the fact that they are gapless is not immediately clear because I've just drawn a state, but I mean, at least there are two modes. Two gapless spin 1/2 modes at the boundary. Mm-hmm. Of this state? Okay. Well, the first, okay, yeah, sure. The first thing you're doing, you take your lattice. This is the white stuff. This is a lattice in principle of spin 1s. Okay? And this is my site I plus 1, I plus 2, and so on and so forth. Okay. Then what do? Instead of considering spin 1s, you consider spare, you essentially decouple each of these spin 1 into two spin 1/2s. Okay, the Hilbert spaces do not match, so you have to be sure that you are working also only on the singlets here, so there will be some projectors. Okay? The key point is that you create this ampere spin 1/2s. Okay? And then you define a state where each of these guys is actually paired. Yes. So you have local singlets pair here, and on the top of that, you have to imagine that you apply a projector where each of these pairs is also in singlet, because you want to guarantee that this is a meaningful spin 1 state. And then if you do that, you notice that there are only decoupled edge modes, the decoupled spins at the edge. Okay? They do not enter, I mean, somehow they are uncoupled in this state. They're left alone. They can be whatever value, either 0, or either -1 or +1. Okay? And then out of this simple representation, you conclude that if I am periodic, I have to also couple these two, obviously. So I have to guarantee that they're also in a singlet, because there will be also a projector there. However, if I'm open, instead, these guys are left unpaired, and I have edge modes. Okay? Questions? Okay, so then the non-trivial fact is actually that this state is somehow adiabatically connected to the Haldane phase. Okay? So this was not clear at that time, because what I've done, I've just introduced an artificial many-body operator in my Hamiltonian, it's not clear that beta equal to minus 1/3 is not separated by any phase transition to the value beta equal to 0, which is the Heisenberg model. Okay? This was shown later by means of simulations. Okay, so we are somehow essentially exhausted the list that I promised you yesterday about the Haldane phase. We will not discuss the entanglement properties because we are running out of time. Now we want to see whether this is realizable or not. Okay? So before we go to the more experimentally oriented part, are there any questions? Yes. Yes. This is the sum of projectors. Imagine that you have your spin chain. Okay? If you take two spins here, each pair of spins, these are two spin 1, so they can combine in different ways, and you can write down a projector into the subspace of spin 2 of these two spins, and so on and so forth. So I and I plus 1 is somehow the projector of the state of spin 2 of each pair of sides Si plus 1. Okay. Now, we want to see how we realize that. I mean, in principle, you will think that the Heisenberg model is something very simple. It's actually not so easy to realize it, but there are at least two ways one can think about it, okay? So the first one is to use what we call cold atoms in optical lattice. Questions, yeah, please? That's correct. That's correct, because each spin 2 that you have will pay an energy cost. What you can show is that if you make a triplet at some point, you don't know how to rearrange the next spin 1/2 in order to have it with 0 overlap with the state of spin 2. This you can show by just algebraic manipulation. So every triplet that you put will violate this constraint, this projector constraint. So in this sense, this is the way you show that this is energetically unfavorable. So there is no way of rearranging it if you want. Okay, so the first thing is atoms in optical lattices. Were really atoms or molecules. Well, what is an optical lattice? I mean, imagine that you have a laser which is retro-reflected in a proper way. This creates a standing wave. And depending on the polarizability of your objects, the atoms will like to live either at the minima or the maxima as this laser beam. Effectively, what you have is a band structure. Okay? And essentially, this is described when you second quantize it as a Hubbard model, or a Bose-Hubbard type model. Let's suppose that we are working with bosons for a moment. Okay. So this is the easy part. Now you have to see which kind of terms you have in your Hamiltonian, okay? There will be typically two types of terms. The first one is tunneling. Now B's are now bosonic creation and annihilation operators at the site I. So that's the first term that you have. Wow. Then the second term is just interaction. So when two atoms sit on the same side, they will interact. This will be something like U, sum over I. There is typically U over 2 for normalization purposes, and 9 minus 1. This we denote in green. And that's typically all you get. Okay, so if you trap atoms like rubidium or cesium in an optical lattice, this Hamiltonian is to a very, very good approximation, the one that is realized microscopically. Now, can this Hamiltonian somehow be related to a Heisenberg model? Somebody say yes? Okay. Well, maybe yes, but it will not do what we want, so to have something which is an isotropic Heisenberg model. Okay. What you need for that is to add an additional nearest neighbor interaction. Sum over I, and I plus 1. Something if you have two atoms, they can interact also at a finite distance. Okay? And this is typically, well, it's typically not appear, or if it's appearing, it's very tiny. Because if you take two atoms, their interaction is of van der Waals type, so it's extremely short-ranged. Okay? You will have only local contributions, but you will not have no local ones. However, there are additional interactions with atoms which can be of magnetic origin. Okay? There are some atoms which have very large magnetic moments. For instance, dysprosium or erbium, chromium. Okay? They have large magnetic permanent magnetic dipoles. And this way, they actually can have a finite interaction even at finite distances. Okay? It's of magnetic origin, so this will be decaying as 1 to distance to the third power. It's a dipole-dipole interaction. Can also have certain angular dependencies, which we are not interested in because we're working in 1D only. The key number you should remember is that this interaction scales, V, typically, they are of order between 10 to 100 Hertz, maybe 200. They will depend also on the lattice spacing. Yeah? I mean, the smaller the lattice spacing we can make, the larger this interaction is. Okay? Making a very short lattice spacing is tough. Okay? You cannot go arbitrarily close for several reasons due to light-matter interaction. I would say that the smallest lattice spacing that people can do nowadays are of order of 200 nanometers. Okay? So this is more or less the boundary. So this is not an energy scale that we can crank up as much as we want. So it's limited by certain factors. Now, do you remember how many nanokelvin is more or less this number that I've put there? That's roughly 5 nanokelvin. Okay? It's already telling us that this is not immediately easy. Okay? It's possible, but you have to cool your system very well. Now, there is an alternative way of getting long-range interactions. There are two alternative ways of getting long-range interactions in this kind of systems. The first one is actually not to trap atoms, but to trap molecules. Okay? Molecules can have permanent electric dipole moment induced by an external electric field, like rubidium potassium. This is a typical molecule, rubidium cesium. These dipole moments, they don't have universal values because they depend on to some extent on the applied electric field, but they have a maximum value. And they also have interaction which are R to the 3. And their energy scale is instead much more favorable. It depends on the molecule, but I would say it's between 100 and maybe 2 to 3 kilohertz. Okay? So these molecules have definitely stronger interactions. Yes? Yes, you have to use an external electric field to let the molecule choose a quantization axis. Yes. So in principle, you have this big dipole, but it's not oriented. You put an electric field, you orient it, and this will have a certain angle, theta, with respect to the direction of your wire. Now, this angle now matters, because if you have dipoles which are just oriented in this way, so when this theta is equal to pi, they have the maximum repulsion. Instead, if you put this theta equal to 0, then you have the maximum attraction with a factor of 2. Then there is, in addition to that, a magic angle, theta magic, so I think it's around 58 degrees, where this interaction is actually 0. Okay? So in principle, by just changing the quantization axis of your dipoles, which in the experiments is just changing the direction of an external electric field, so it's not difficult, you can change almost at will the strength of your dipolar interaction. Sorry? You can have them, so like you can have also off diagonal terms, which are not of this type, obviously. Yes, actually, I would say the first experiments that have been done convincingly in a many-body sense have been done through these transverse terms, like S plus, S minus. These are really full spin models. But the problem for this kind of terms is that typically you only get spin 1/2 Hamiltonians. Okay, you can also get spin more than 1/2, but this is challenging technically. Okay, so this is more or less to give you a brief view of what one has to do in the experiments. I mean, either take some of these magnetic atoms or take polar molecules, and this will be the interaction strength that you are reaching. But I've not shown you yet that this is what is called extended Hubbard model, has anything to do with the Heisenberg model. Okay? Actually, the reality is that it does have a lot to do. So let us now fix, for instance, the filling fraction to 1 particle per site, and have a rough view on the phase diagram of the model. Okay, here we put U over T, and here we put V over T. Now, when V equal to 0, so along this line, it's a well-known fact that there is a phase transition at some point which separates a superfluid, which is there for very tiny interaction, to a Mott insulator. That's a Mott insulator. Okay? And the Mott insulator, the cartoon state for this guy is just we have a single atom per site, and that's it, because he wants to minimize the local energy U. Okay, and we are at filling 1. This is the only way of doing that. Now, let us suppose that we are working at very large U and we start increasing V. Is the Mott insulator always the most favorable state energetically? Obviously not. Okay? The Mott insulator has 0 energy with respect to U, but for each pair of particles which sit on nearest neighbor, we pay an energy cost V. So its energy is V, classical energy, is V times the number of particles. You can't avoid that. Well, but at some point, it is kind of obvious that it would be much more favorable to actually stack particles on the top of each other in order to avoid V. Okay? And a state of this type is kind of what we will call a charge density wave, quotes. And this will have energy V times the number of particles over 2, because it's V times the number of pairs. Sorry, not V, U, obviously. So at the classical level, there is at some point a phase transition separating these two phases, which is at the value of V equal to U over 2. Okay, that will be V equal to U over 2. Now, what happens in this full phase diagram is that actually there is a Mott lobe, what is called superfluid lobe here. If you look really into detail at the quantum phase diagram, is at some point this phase transition, when you start coming close to the quantum limit, so when you start having t comparable to u and v, actually opens. Okay? And what happens in this region of space is actually simple to have a look at. I mean, what is the local Hilbert space if we consider states which are close in energy to this charge density wave and this Mott insulator? Well, the local Hilbert space contains only empty sites, sites with a single particle, and sites with two particles. Okay, this is everything which is needed to describe these two states. So you expect that the region in the middle, which describes the competition between these two terms, is captured locally by an Hilbert space which contains two particles, one particle, and empty. Well, but that's simple to map into an Hilbert space of spin 1. So the effective low energy description of this, in principle, Bose-Hubbard model, so with infinite local Hilbert spaces, in the vicinity of the transition between a Mott insulator and a charge density wave, is more or less described by an Hilbert space which has a spin 1. Now, if you start looking at this Hamiltonian on top of this Hilbert space, you can actually show that the effective description is the Heisenberg model plus some corrections. And the corrections are due to the fact, simple fact, that while in the Heisenberg model there is an exact up-down symmetry, okay? In the Bose-Hubbard model, there cannot be an exact up-down symmetry because there is so-called bosonic enhancement. Okay, so B dagger is not equal to S plus as an operator, as a square root of 2 at some point, right? So that's the origin of these discrepancies. Well, that's not particularly important. It can be shown both numerically and analytically using a technique which is known as bosonization, that this phase here is the Bose-Hubbard equivalent of the Haldane phase. Okay, and it's actually quite broad. This was shown by several people, I think, Dalla Torre. It's PRL 2006. Okay. So in principle, even if we cannot realize directly the Heisenberg model, because we don't know immediately how to realize a spin 1 model, what is possible to do is by just considering simpler question. You mean here, close to equal to 0? Yes, up there it closes. Up there it closes. You can understand it as follows. Okay, there are two ways of understanding this. No, actually, this is not happening. So there is a fixed value of u upon which this phase exactly closes. I mean, within the accuracy of numerical result that we have. And the understanding of this closing is as follows. Do you remember that before I told you, in this spin language, it's like having a spin up, then a number of zeros, and a spin down, numbers of zeros. This is the description of the Haldane phase. But this is, then you can, if you want, with a bit of wishful thinking, adiabatically connect this with the null phase. The null phase is the one, you count the average number of zeros between a plus and a minus. Okay? And in one direction, in the direction of the null phase, at some point this number goes to 0. Okay? So by studying this effective number of zeros with an effective field theory, which can also be a free theory, you show that there is a critical value of u above which this critical number of zeros is always 0, so you cannot have a phase which has a dilute antiferromagnet, as only null order or as no order at all, which is the Mott insulator. And this you can do with simple modeling, yeah? And then obviously if you want to have something fully non-perturbative, you have to show it numerically. But there are simple physical arguments that indicate that this phase is finite. The critical point is actually not so clear. Okay? And this is also reminiscent of what is called lambda D model, which is an extension of the Heisenberg model. as some critical lines, as the same phenomenon. At some point, the Haldane phase closes. And there it's actually debated if the critical point has an emergent supersymmetry, because it's at the junction between an Ising phase transition, C equal to 1/2, and a Gaussian phase transition, C equal to 1. And in principle, these two can merge, get what is called conformal fluidity with central charge 3/2. But then central charge 3/2 has a lot of different meanings, can either be just a very non-interesting sum of the 2 degrees of freedom, or the 2 degrees of freedom can be entangled in funky ways, and there is one way of getting also emergent supersymmetry there. But I mean, this is an open point. I don't know. I don't think in this context this has been solved. U0? U0 is very pathological, because you see, if I take U0, I can put as many particles I want on a single site. So in any experiment, there would be what is called collapse. Okay? Here, I mean, it's essentially impossible to study. That's the problem, because maybe you can do Bosonization at exactly U equal to 0. This will also not work because the spectrum is non-linear. I don't think there is really a reliable method to study this, to be honest, so I cannot comment. That's a good question. Yeah, in principle you can ask, okay, maybe I want to have a spin 2. Within this construction is not so easy, because this is a construction that is based on contrasting a Mott phase with a density wave. So this immediately tells you that the number of degrees of freedom is limited. Either you have something which has the equivalent of your 0 and the spin, and on the other side you have the equivalent of the plus and the -1. In principle, you can say take a filling 2, and then you will have here 2's, but here you will have 1's and 3's. So this will not allow you immediately to get the spin 2. If you want to have a spin 2 theory, you have to play more tricks, which is either do a bit of fine-tuning, because if you fine-tune, you can still find a local Hilbert space which has more than 3 states. Or you can completely give up on this and use other degrees of freedom. Actually, for spin 3, I will know a way of doing that, because there are some of these magnetic atoms which have a large spin, and you can play with them and get spin model. I mean, for instance, erbium, there are some fermionic isotopes which have spin 19/2. So if you want to have a spin chain with spin 19/2, then I can tell you how to do it. Okay? But it's important that this is just coming out of atomic properties, and it's not very easy, if I give you a manifold of 19/2 Zeeman states, to actually cut some of those to have a spin chain with a smaller spin. For 2 reasons. First is that the S plus creation operator actually is obviously changing as a function of the main spin. So if I take an S plus of a 19/2 and I project it only on, I don't know, 4 or 5 states, this is not S plus anymore, as a strange matrix element, because the Klebsch-Gordan coefficient do not match. This is the first problem. And the second problem is also technically not so easy to isolate the Zeeman spin states in an efficient way. It's possible, but it's not so easy. Anyway, okay, so that's the phase. I mean, then there is the question, we're doing the time, okay. Then there is the question, if one gives you this model, how do you show in an experiment that there is an Haldane phase? Well, in principle, you can provide some indirect evidences. For instance, you can look at the gap. We have shown that there is a finite gap. You measure it, and you say I have a gap at phase. The advantage of cold atoms is that you can also have a look at the order parameters. Okay? So we were mentioning before that we had this order parameter. Let's see, OZ, for instance. This as a function of the microscopic spin. This is a correlation function. And here we had the sum of the SZs, K, SZI. Now, the tough part of this order parameter is obviously this object, is the string. But then when you look at this string, you immediately realize that as a very, very simple interpretation. I mean, this string is essentially counting a +1 whenever there is wherever there is a spin 0. If I have a spin 0, this is +1. If I have a spin up or a spin down, this counts -1. Okay? But this is kind of a parity measurement, because this 0 was a single particle in my microscopic realization, while this up and down, they were just either 0 or 2 particles. This means that if I have a mean in my experiment to check what is the parity of every single site in my system, then I can measure this expectation value. Okay? Or at least I can measure the expectation value of the string operator, to be more precise. Well, it turns out that there are methods for doing that. Okay? And in particular, this goes nowadays under the name of quantum microscope, quantum microscope. So since I decided not to use the computer at all, I cannot show you funky pictures, okay? But there are. A question, please? No, these are more or less, I would say, rather conventional transitions. Okay, so this one I think is a yes, but the edge states at the very at the transition point, the gap is so tiny close to the transition point, the edge states you can almost not see, because when the gap is so tiny, the wave function of the edge modes actually sneaks into the bulk. And especially at finite size, you will actually not be able to recognize those. Okay? So if you want to see the edge states, you have to dive in the middle of this phase, where the correlation length is as small as possible, and then, depending on the system size that you have, you might be able to see them or not. It's also not an immediately cheap thing to do. Okay? Because if your edge, if the minimum correlation length that you can have is like 10 sites, but your system is 20, it's not too easy to distinguish what is in the edge and what is in the bulk. Okay? So you want to have a very clear-cut separation of energy scale to see those. Luckily enough, there are some points in this phase line where the correlation length over a few sites, like 4 to 5 sites, this means that a system of 20 sites, 30 sites, can actually see those. At least if the temperature is much smaller than the coupling strength that we were mentioning, which is also a challenge. Anyway, what I was, we were discussing this string correlation function. So what people nowadays do in the experiments, they can measure parity locally. And the way they do it, they just have their system dynamics, and at some points they freeze the dynamics by just ramping up the lattice. Okay. At that time, whatever number of particles was there, the wave function is frozen. Okay. And then in order to image every single site, what they do, they use what are called fluorescence techniques. So they scatter photons on the top of the atoms. However, there is a bad effect coming up, that if you have a single atom, this can scatter a photon and then can show you that it's there. If you have nothing, you don't see, you can't see anything. However, if by chance there are two atoms, what happens is that when you inject photons in the system, the two atoms can actually react. Okay, because they can absorb energy, and if they react, they are immediately released from the trap. So essentially, when you use this fluorescence imaging, 0 gives you 0, 1 gives you 1, but then 2 gives also 0, because the atoms are lost. 3 will give you 1, because the first photon scattered two particles, they are lost, but there is one remaining. 4 gives you 0, and so on and so forth. So actually what they can do in experiments, they cannot at least easily measure the number of particles. They can only measure the parity, but it turns out that the parity is exactly what you need to get these string correlation functions. Okay? Somehow it's a lucky coincidence. Essentially, because, these photons, they give them a very large energy. So if there is a single one, the only thing you can do is trap it in a very, very tight potential. So you can increase its energy, but it can't escape because there is no chemistry of a single atom. Right? When you start putting light on more than one atom, chemistry plays a role. And this means that the light that you use to trap the atoms, in case you have recombinations like molecules, it's not guaranteed that this molecule is trapped by the same light because there's a different spectrum. It's completely different. Then typically, since you are not guaranteed, this is not trapped, simply, okay? Or maybe it's trapped only weakly, and then it's hot, and then it leaves the system. So now this is what happens there. Nowadays, there are a bit more clever techniques, like developed in the group of Greiner, where what he does, he performs the experiment, and then he tries to split the lattices, the lattice in two lattices, such that it doesn't count the parity, but it can count the parity modulo 3. So you can count 0, 1, and 2. But this is already much more complicated. I mean, the simplest version of what we call nowadays microscope is not something that tells you the number of particles, it's something that tells you the parity. Okay. Yes, but then, once you stop the cooling, you live with these particles, okay? Then you do your dynamics. Sorry? Well, but this is okay. Because somehow, at this point, you're already in the measurement part of the experiment. So you have your dynamics, you have your ground state that you have realized. Then you have to measure it. You measure it destructively. So you ramp up, you do something to the wave function, and then out of this something, you reconstruct your correlation function. Okay. Okay, I would suggest that we stop here. Yes. Then, after the break, I will tell you a bit more of another way of realizing spin models with cold atoms, which is based on what is called Rydberg dressing. We will see it very quickly. And then we start the discussion on topological superconductivity. I mean, unless there are urgent, or there is one urgent question. Uh-huh. Yes. This would be, okay, this is another thing. I mean, how can you, well, the these singlets are made out of spin 1/2 out of a spin 1. So you want to have a measurement on the top of a spin 1 that sees if there is a singlet there. Okay? This is not so easy. Okay? Second thing is that it is true that I told you that for this simple ground state wave function. But that ground state wave function had also correlation length essentially 1. It was almost a product state. The ground state of a microscope, this will never have this structure, okay? You have to look at other parameters or global quantities to see that. Uh-huh. Well, I would say, I mean, first there is a kind of a, in my opinion, historical importance. So this is really a paradigmatic example of a topological phase, and despite the fact that people have actually observed some of these properties in magnetic systems. For instance, the Haldane gap was observed, and this was actually one of the reasons, I think, why Haldane got the Nobel Prize. If you read the extended synopsis, it discusses all the sigma models and discusses also the fact that this Haldane gap was observed as a really remarkable discovery. On the other hand, I mean, why do you want to do it with cold atoms if somebody has already seen some key properties with other systems? I think the point is you want to use it as a kind of a toolbox to understand what the potential of these cold atoms is. For instance, I mean, measuring non-trivial, highly non-local correlation functions in a topological state. This is remarkable because this is really somehow telling you cannot describe this state otherwise. Okay? Then you can say, okay, I want to do it for technological applications, like there is this discussion of topological quantum computing and so on and so forth. In that sense, I don't think the Haldane phase realized with cold atoms will provide any boost to the field, in the sense that it's true, it does have topological properties, it does have topologically protected edge modes, but from this simple observation to say that this is useful to build something which is topological quantum computing in 20 years from now, I would not say. So my interest is fundamental. Okay, there are really some paradigmatic aspects that nobody has ever shown in an experiment, which I think it's an important thing. More urgent questions? Okay, then we reconvene in 10 minutes. Okay, here we are back. There was a comment I wanted to make, which I forgot, and pertains what I was telling you in the last hour. And there is a reason why I put it here one, and this is not the only thing I wanted to show you, but then I forgot the second one. The second one is actually that there have been, like in the last 3 to 4 years, experiments studying spin models in atomic systems which depart quite far from the conventional optical lattice ideas. Okay, so these are experiments where the atoms are immobile, and where the interactions are actually just generating the full dynamics. And maybe you have seen that there was a paper published a few months ago with a provocative title like "Quantum Simulation of 51 Qubits." Some of you have seen it, some of you have seen it, okay? So maybe I spend 1 minute to tell you about this idea for two reasons. First, because I find it very elegant, and the second is that it's actually quite simple. Okay? So the idea that these people had to realize, the goal was to realize spin models in atomic systems, okay? And these people, and there are two groups that are currently leading this effort. One is the group by Antoine Brevet, which I for sure misspell. I think it's like this, okay? In Palaiseau. And the other is the group by Misha Lukin, which is harder to misspell, so I think it's correct. And what these people are doing are putting atoms in what are called optical tweezers, okay? So essentially they are trapping atoms via light, and the key difference between optical tweezers and optical lattices is that while the optical lattice is actually a fixed lattice, so it's there, you shine a laser and it's there, these tweezers, they are actually movable, okay? So they are at distances which are much larger than the typical optical lattice experiment. So they have certain configuration of these tweezers, they traps. These are typically of order of few microns, okay, like 2 to 10 microns. Okay. And then they try to load atoms into these tweezers. However, you can imagine that the loading of a single atom in a potential, this is not an easy thing. What do you think is the chance that when they want to load an atom, the atom is really there at the very end? It's not a difficult number, and it's not pi. It's 50%, okay? So in principle, if they just do their experiment in a naive way, they will really not realize a spin model. They will realize a model where there are spins on 50% of their sides, but there is an empty side on the other 50%. I mean, this can actually be an interesting thing to study, for instance, percolation, thresholds, and all these kind of things, but it's not something that you want if you want to study a Heisenberg model, okay? So what these people have been able to do recently, they are actually able to fully rearrange the system. So, first. Well, essentially because if you start loading more than one, you don't want to have more than one atom. You want to have at most one atom. Okay? So this means that you are trying to load these atoms in the traps. You cannot overload them. Then there is no other chance. Deterministically, it's a... Well, I mean, if you have only two chances, which are 0 and 1, then it's 50-50. Okay, I mean, I think I can tell you more in detail later on. Okay? It's actually not exactly 50, but it's very close, let me say it like this. Okay? So the problem is that they have this lattice which is only partly loaded, so they have to do something. Yeah? And what these people nowadays are able to do, they are able to rearrange their tweezers, the configuration of their tweezers, so that the traps where there are no atoms, they are essentially cancelled from the dynamics. And the traps where they have the atoms, at the beginning they are in very different positions. For instance, here there is something. And then they can reshape this lattice such that at the very end, they are only left with these four sides. Okay? And now they can do it in 1D. This was the experiment by Lukin, and in the experiment by Brovet, they can also do it quite easily in 2D, and even in 3D. Okay? Now, I can't really draw it efficiently, but I mean, I think I've seen pictures of Kagome and pyrochlore lattices here. I mean, it's actually something that you can do with a very large degree of flexibility. Okay? Now, I mean, there is a problem, which is intrinsic in this number that I gave you now. Okay? These distances are, let's say, 2 to 10 microns. And we have said before that the typical distance of optical lattice experiments is maybe alpha micron, 200 nanometers, something like this. So if you try to use the same interactions that we were using before, remember they were decaying 1 over r square. Let's say there is a factor of 10 difference. This means that there is a factor of 1,000 difference in the interaction energy scale. Okay, this will be interaction of 1 Hertz. 1 Hertz. First, it means that you need to have coherence time of at least several seconds to see anything. And second, means that your temperature has to be really, really small to see anything. Okay, so the conventional interaction that people use in cold atom experiments here are useless, cannot be used. So the idea is that in these experiments, what they use are interactions used by Rydberg states. Well, Rydberg states, to make a long story short, they are very highly excited state with a very high principal quantum number, typically above 30. And you can imagine this state of alkali atoms as taking one electron and pulling it very far from the nucleus. Okay? So this way, this is kind of a gigantic dipole for atomic scales, and this has huge interaction, which scaled with the n, the principal quantum number, to the power 11. Okay? So they can really be large. For the purpose of these experiments, these effective van der Waals interactions, they are of the order 10 megahertz, a typical distance of a couple of microns. This means that, I mean, this is much faster than anything else you have in cold atom systems. There is a price to pay when you do this. Is that since you are using highly excited states, it does happen that these guys actually do decay. Okay? So there is a limited coherence time, which can vary. I mean, this is, I think for this the experiment we're talking about, this is of the order of 10 microseconds. Okay? 10 to 100 microseconds. So you have this limitation. But the ratio good versus bad here is still of order of several hundreds. Okay? We have 10 megahertz. So these are something that happens at the 0.1 microsecond scale, and you have to have something that has to happen before 10 microseconds, so you are safe. Okay? So these are dissipative, in principle, dissipative experiments, but you run them so fast that you don't see this dissipation. And what these people have been already able to show is that you can look at devil staircase kind of phase diagrams of simple spin models. And the idea is that this kind of settings with very few tweakings, they can actually be adapted to study spin 1 models. So far it was only spin 1/2, and there were 2 papers by one by Alex Gletzle et al. And the other one by Eric van Buyden and Thomas Paul. Both of them versus PRL 2015 that show specifically how you can do spin models in this kind of settings. You actually don't use the full Rydberg interaction. What you do is you only partially adjust to the Rydberg state. This obviously decreases the interaction strength, but at the same time also increases the coherence time. But what is important, this allows to have almost arbitrary low spin models, Heisenberg type models in this kind of settings. Okay, so this was just to show you that optical lattice is definitely not the end of the story. There are new, exciting experimental avenues, and I think topological metric is definitely one of the immediate applications for this kind of things. Okay, with this, we can now forget about the Heisenberg model. Okay? And we go to the, I mean, there are other questions. I mean, this was very qualitative, but I don't want to really dive into details because it will become messy very quickly. If you are interested in the atomic physics details of that, you can just let me know and then we can discuss. Mm-hmm. Well, it's 1D, so the transition, if it's gapless and it's relativistic, this has to be conformal invariant. The transition between the Haldane and either the Nel phase or the Mott. And then once you have the constraint of being conformal invariant, actually there are not many possibilities. But that's okay, because in 1D, very often you cannot do it. You can write down a convention, I mean a CFT action, and that's it. And the reason is that there is not really another parameter in one of the so Landau-Ginzburg in 1D, this requires some symmetry breaking in principle. So that's okay that you cannot write it. No, actually one of these two transitions will have exactly the same properties. So we'll have exactly the same entanglement properties, for instance. The same critical exponents. But yeah, this is not a problem. The low energy fields, they are the same one as the Ising model for one of these two transitions. Does not, well, the topological nature of one phase and the simple, I mean, the product state nature of the other phase do not imply that in the middle there is an exotic, there is an exotic transition. It can be a conventional transition that you can also find in a Ising model. Yes. I mean, because once you fix the central charge, you do not have freedom to change the exponents. Almost. Okay? So if it's equal to 1, you have. For this specific case, yes. There are other cases. For instance, if you go to more than one dimension, there is this scenario of deconfined quantum critical points, which has been put forward by Sentil and other people more than 10 years ago, which essentially tells you that if you have two phases which are described by symmetry breaking but with incompatible order parameters, classical theory of phase transition tells you that either the phase transition is first order, or if it's second order, it is due to fine-tuning. Okay? That's the these people actually propose a different scenario where essentially there is a gauge theory degree of freedom that becomes relevant. It becomes the meaningful description at the critical point, and this get deconfined. This is why it's called deconfined critical point. And it's not so easy actually to find this in microscopic models. But I think there is a model, which I know of, where this is more or less conclusive that this transition exists. And this model, on one of the sides of the transition, has a topological phase. So if you want to dig something somehow exotic in quantum criticality out of topology, I think I know at least this example. But this is more than one dimension. It's in 2 dimensions. And this model goes under the name of Balance, Fisher, and Gervin. It's a strange model with anisotropic interactions, but in principle you can study it, and you can show this. Okay, I forgot where. Okay, no, new topic. Are there other questions on this Heisenberg model part? No. Okay, good. So let us go to topological superconductors. Now we will kind of make a small change of paradigm now, and we will be looking at models of fermions. Okay? And in particular, we look at a model which is so-called 1D p-wave superconductor, and also goes under the name of Kitaev wire. Or Kitaev chain, or don't call it Kitaev model, because then it becomes less ambiguous. There is also a 2D Kitaev model, which is completely different. Okay? So, and the idea is that we take a lattice, 1D lattice, of spinless fermions. So our degrees of freedoms are AJs. Okay? And we define the following Hamiltonian. Minus T. We have a tunneling. Let me take the system with open boundary condition for simplicity. AI plus 1 chain conjugate. We have a chemical potential. I. And then we have a term which describes superconductivity, which we call W from I to 1 to L minus 1, and this term is made in this form, A dagger I, A dagger plus 1, plus emission conjugate. Okay? Okay, how do we understand this model? I mean, this is just describing tunneling of particles. That's a global chemical potential. The interesting term is this fellow here. What is he doing? He's taking pairs of particles and moving in and out of the system. And what does this represent physically? Well, physically it represents the presence of some p-wave superconductor that is actually very close to this wire. And this p-wave superconductor here, let me call this A bars. These A bars are condensed, like in a conventional superconductor, and can be exchanged with our wire. That's the physical interpretation. And this strength here, W, is given by the condensate fraction of the superconductor. Okay? They are related. Okay? Now, you immediately see that this model has one feature, which is a quadratic fermionic Hamiltonian. Okay? So we will be able to tell a lot by doing very simple calculation out of this. However, before doing the calculation, I want to emphasize the role of one factor, which is symmetries. Okay? Now, this model has what is called parity symmetry. This means that if you take the Hamiltonian, this commutes with the parity. The parity is nothing but the product over all sides of 1 minus 2 and I, where n and I is equal to a dagger. I obviously is a number operator. So maybe I should not prove this, because you can see it from what I've written. It is not possible to act on a state with this Hamiltonian operator and change the number of particles modulo 2, which is the parity. Okay, because this guy does not change the number of particles. This guy also does not change it. This guy changes the number of particles, but he changes them only modulo 2, which means that the parity of the state is preserved. Okay? So this is the case where you have a symmetry, you don't even have to do any calculation to show this. Now, what is the, I mean, sometimes, maybe some of you have a high energy background, you have heard that the parity symbol is something fundamental, okay? What do we mean here by fundamental? I would not go so far to say that this is fundamental, but it's definitely something which makes a lot of sense in any physical system. Because imagine that you want to write down a perturbation to this Hamiltonian operator, and you want to write something which is like a dagger. Does it look like a meaningful perturbation? First thing you check in Kitaev's original paper, and it tells you that this is not reasonable, okay? And this you should really believe. But there is a, in my opinion, simpler physical interpretation. I mean, if you have a term of this type, this means that on the other side you are tracing a degree of freedom where there are fermions in odd number which do condense. Okay, you imagine that on the other side there is something like an A which is condensing, like an A bar which is condensing. I mean, is it possible to have a condensate of? Obviously not. Okay, so okay. So that's the reason why, simple reason why fermionic parity symmetry, it's somehow something which is very reasonable. Yes, but still you cannot write a term like this in the Hamiltonian. I mean, you will have a lot of single particle states which are gapless, and at some point one of your particles can move there. But you still have to consider the bath as a dynamically, like these sides dynamically. You cannot integrate them out of the description. Yes? Yes, but then you cannot integrate it out completely, because, for instance, the symmetry of the wave function, if you integrate that out, will change when you apply a single fermionic operator, and then you're violating the rule of the game. No, if you carry that alone, then it's absolutely reasonable to have a term which is like A dagger B, and your B is just sitting here and doing nothing. That's fine. But this is not the model that we are talking about. It's a model where the Hilbert space is defined with the 2 to the n. And I'm not allowing the Hilbert space to be larger. Like, for instance, by putting another degree of freedom. No, actually, no. Well, but then it will not be an A dagger only operator, it will be an A dagger times B. No, if you remove the B, you cannot do this. Because if you remove the B, this means that you are integrating a part of Hilbert space out, and you will not get the A dagger, absolutely. There are no tricks here, no. Can't do that. Yeah, but you are integrating out a part of the dynamics which you can't do. Because this means that you are saying that certain states are equivalent when they are not. I can give you a simple example. Okay? If you integrate out the B's, there will be some state here which have a B, and some state here which do not have a B. Now, in the states where here there was a B, you can act with this, you cannot act with this operator. In the state where there wasn't, you can. But if you integrate out the degree of freedom, you don't know. So there is no way of legally integrating that out, and at the very end, leaving the A dagger. The only thing, the only way around this, to have a term of this type is to have it in a Liouvillean as a jump operator. Okay? If some of you are familiar with open quantum systems, if we forget about Hamiltonian descriptions, it's actually possible to have an A-dagger. Liouvillean, there are no constraints. And this means that dissipation, in principle, one has to be careful when making statements about parity. But as long as our system is closed, we can think about it as a kind of very robust symmetry. Okay, so this is as far as symmetries, and so the insight from Kitaev is that it's not only this simple system soluble, but actually has interest in physics. And in order to show this, it's actually useful to introduce what are so-called Majorana operators, or real fermions. And the procedures works like this. Now, let us take our lattice and we do something similar with respect to what we have done before with AKLT. Okay? At every site, remember, initially, we have an A and an A dagger. Okay? At the site, let me call it J. Okay. Now, we decompose the fermion into two half fermions. What are these half fermions? Well, what we do, we define define an operator which is C2J. Now, let me use the precise definition of Kitaev so that you can look at this paper. This is AJ minus A dagger J over I. Okay? And then we take another one, which we define as 2J minus 1. And this is instead A dagger J plus AJ. Okay? This is just formal manipulations. These are 2 degrees of freedom. And we can do that at every site in our system. Now, you notice that these operators have actually 2 interesting properties. The first one is that what happens if I take the dagger, for instance, to C2J minus 1? Nothing. It's the same operator, right? Okay. C2J minus 1. And the same happens for C2J. The other striking fact is that if you look at their commutation relations, let me call it CM, CL, they actually satisfy the following rule. This is 2 delta LM. So they look like fermions, but they are not. Okay, there is a 2 here. And you don't believe it? You can try and check. You can redefine them. That's okay. Okay, but do you really like this? Okay, so yes.
I think the reason why it's not fermion is you cannot define Fock space for it. So it's not like a real particle.
The first condition is the most important one.
Yes.
That this is actually a real operator and not a complex operator. Okay? So you were fooled by these 2, but the important information is actually here. The important information is here. You can rescale it here, but it's not important. Okay? So the combination of these rules actually satisfy what is called Clifford algebra. And we will see tomorrow how these interesting braiding properties. Okay? Now, what is it? Why is this description actually instructive at all? Well, it is instructive because it allows us to understand the phase diagram of the model in a very simple fashion. So we can distinguish by just fine-tuning the Hamiltonian parameters 2 phases. Now, the first phase, if we just take the chemical potential larger than 0, and then we take the tunneling and the superconductor strength to 0. Okay? Obviously, the ground state has no fermions, right? Okay? There is no term is chemical potential larger than 0. Okay? What happens, though, is that you can rewrite the Hamiltonian, even in this very simple case, as a function of your Majoranas. And this reads as something like this. This would be 2j minus 1, C2j. Okay? And the sum, this is important, goes from 1 to L. Yes. This means that in this phase, there are no fermions, and this means that locally, there is only pairing between pairs of Majoranas. Okay? There is no entanglement, it's a trivial state. Now, if I show you this, it means that in this description there will be some other state, which is more interesting. Okay? And this is actually the case. If you now put instead the chemical potential to 0, and then let me allow a bit of fine-tuning, and we fine-tune T equal to W. Okay? We go to this specific point. So what happens to this specific point? We can rewrite the Hamiltonian. It will be minus T, sum over I. Okay, we can rewrite the operators one after the other. So you have to invert this relation. So we want to have the formula for A dagger I, so A dagger J. A dagger J, you take the sum of these two Majoranas, actually the difference, C2J minus 1. Okay. Plus I, C2J over 2, something like this. To have A dagger. No, there is a minus. Okay? And you do the same stuff for A. You rewrite everything here. I think we cannot make it, yeah? So we will skip directly to the solution. Well, the solution is that you get something, which is IT, and then you have an exotic term here, which is J from 1 to L minus 1, C2J plus 1. Okay? Notice it is important that I have now specified the indices of this sum. Okay? It's very, very important. And I'm assuming open boundary conditions. Okay? Now, if I now want to visualize this Hamiltonian in this simple picture, let's see how it's made. Let us take just a system of 4 sides. Here we have C1, C2, C3, C4, C5, C6, C7, C8. Now, this Hamiltonian contains the first coupling is the one between 2 and 3. Then we have a coupling between 4 and 5, 6 and 7. However, C1 and C8, so C1 and C2L, they do not appear. Okay? They're completely out of the dynamics. And now, this reminds us of what we have seen previously with AKLT. There are some degrees of freedom at the boundary which are decoupled. So this can be boundary modes. But now this is a bit more exotic, because before these boundary modes were just spin one-halves, something we can kind of understand, and we can build a spin one-half also without having to build a many-body system. But here, these objects, they are just real fermions. Okay? So this is telling us that there is a phase, or at least there is a point in the phase diagram of this model, which has decoupled 0 modes. Okay? They're called Majorana 0 modes. Now, we can do a simple check going back to the criteria that we discussed yesterday, is this a topological origin and so on and so forth. I mean, do you remember one of the check was that we should look at the spectrum, and the spectrum of the Hamiltonian should change when we change the boundary conditions. Okay? Now, this is true that there are these Majorana zero modes, so there are somehow decoupled degrees of freedom when we are open. Okay? What happens? Oh, please. You have a question? Maybe I answer it before you ask it. Okay? Let's see if I'm able to predict that. Okay? So let's see what happens when we do periodic boundary condition. But before doing that, we want to be a bit smarter and rewrite this stuff. Okay? Because looking at energetics of real fermions might not be easy, so what we do, we redefine a new set of operators that we call A tilde. And these A tildes we just build not with the pairs of C2j minus 1, C2j, but with the pair C2j, C2j plus 1. So this A tilde j's, the first one is like 1/2, C2j plus I, C2j plus 1. And then obviously A tilde dega j is 1/2 C2j minus I C2j plus 1. Notice what the difference is. Now we had the before we had the pair C2j minus 1 C2j. Here we have the pair C2j C2j plus 1. So this A dega tilde, let me use the green to represent them. They actually live exactly on the pairs of Majoranas which are coupled. Okay? Now, you can rewrite down this Hamiltonian as a function of this A dega tilde, and the final result is that you have T sum over I from 1 to L minus 1 of A dega tilde, A tilde J, A tilde J, plus constants. So the Hamiltonian, which was already simple in the language of Majoranas, is even simpler in the language of these new fermions. We just have a collection of free fermionic sites. Okay? Yes? Yes. Yes, that's correct. That's correct. Formally is perfect. Yeah. Now, the main difference is that here, with respect to the very beginning, we don't have L degrees of freedom active. There will be one of these degrees of freedom that I now call A tilde L. And A tilde L is actually made out of the first and the last Majorana. So this will be 1/2 C2L plus I C1. Okay? But this guy does not take part of the dynamics, because it's not present in this Hamiltonian. Okay? This means that we can understand our state there as a collection of free fermions. Yes, I can do it here. Okay? Times something which is a wannabe free fermion, but is half localized on the left boundary and half localized on the right boundary. Okay? When we do close the system, this also becomes part of the Hamiltonian. Okay? So this is the Hamiltonian with OBCs. If we have the Hamiltonian with PBCs, this will be exactly the one with OBCs, plus T A dega L tilde tilde. So what is the difference in the spectra of these two Hamiltonians? In this case, the ground state has 0 occupation in all of this A dega A tilde. They are 0. 0, 0, 0, 0. However, the mode, which is alpha on the left and alpha on the right, can either be 0 or 1. they have the same energy. Okay? So there will be two degenerate ground states. Okay? And let me stress that this is an exact degeneracy. Okay, they have really the same energy. However, if we work with PBCs, imagine that now we have, instead of a chain, a circle. We will have a circle of fermions, and all of them have to be 0. And there is a single ground state. One ground state. Let me stress it. Okay. So there is a fundamental difference in the spectrum between the OBC case and the PBC case. Now, this looks like we are going into the right direction of showing that there are not only decoupled modes, but they have some topological origin, even though we have not described having a local order parameter, nothing else. But I want to end this question with a provocative, very provocative statement. So is this really true what we have been saying? Because I've shown you at the beginning this simple single particle Hamiltonian, but if we apply what is called a Jordan-Wigner transformation to this single particle Hamiltonian, it can be shown that this maps into the transfer field Ising model, which we know is not topological. Okay? We know it. So, are we somehow misinterpreting these statements or not? The answer to this question will be given tomorrow, so don't ask it now. In the meanwhile, try to think what is really the relation between this model and the Ising model. So if you have not done it yet, it's something that is very useful if you first try yourself, and then tomorrow we discuss together. So, question. That's actually a very good question. We will answer it tomorrow, and it will survive. Okay? But it is obviously a very fine-tuned point. Yes. Other questions? I've not shown you that there is any local order parameter. And I just told you that you can map this model to the Ising model. You should be confused. But that's good. Okay? Think about it yourself, and then tomorrow I show you where is the trick. But don't look at Kitayo's paper for the next 24 hours, otherwise, I mean, you let me come for nothing. Okay, other questions? Okay, if not, we see each other tomorrow at 11. Okay, good.